Okay, our next presentation comes from Samuel Stanwyck, who's from NVIDIA. He's going to be talking, we're entering the quantum stage now in terms of the end note. So we're going to have a great presentation from NVIDIA and from AWS. So Sam's going to start this off talking about accelerating quantum circuit simulations with cuQuantum. Sam, how are you today?
I'm good, Brian. All right, so hopefully you can see my screen now and hear me.
Yep, absolutely. You're good to go.
Okay, awesome. So hello, everyone. It's a real pleasure to be here today. I'm Sam Stanwyck. I'm the product manager for quantum computing software at NVIDIA. And today I'm going to tell you a little bit about what we're doing in the quantum computing space, which in big picture terms is generally thinking about how classical high performance computing can be useful for accelerating quantum computing, useful for the community, and specifically on a product we're developing called cuQuantum, which is a set of libraries to accelerate quantum circuit simulation. So I'll start with a quick overview of some of the basics of quantum computing, where the field is today and where we see it going, and how we see classical high performance computing playing a role. Then we'll get into cuQuantum. I'll go into some detail of what that consists of, why we think it's going to make a big difference, and actually show a couple early performance benchmarks that got us really excited. And then I'll close with an example of why I think this field of quantum circuit simulation has so much potential, and the kind of thing optimized libraries running on GPUs can enable. So this is some work by a group at NVIDIA Research, where they developed a novel quantum algorithm to run the largest simulation ever of one of the most popular optimization problems in the field. Okay, so I imagine there's a pretty big range of quantum computing experience in this conference, and it's a big task to be the one to introduce quantum computing. So maybe I'll just state a few reasons why I think you should be really excited about it. First of all, it's a completely new computing model based on completely different physics. And so a lot of popular science articles, even when they're trying to hype up quantum computing, compare it to other types of high performance accelerated computing, which I think actually kind of undersells this point. So every device for computing until now has been based on classical electromagnetism. This is the first time we're actually controlling and harnessing quantum mechanics, like a more like a different kind of physics. So it's actually something completely novel. And because we're taking advantage of a novel natural resource for the first time, there are bound to be kind of unknown unknowns, and you might expect lots of exciting breakthroughs in the decades to come that can't even necessarily be predicted now, as we get better at figuring that out. So I think although there's a lot of hype for quantum computing in the short term, the long-term potential might actually be undersold. The second point is just how broad and how important the application space is. So the first kind of well-known algorithm for quantum advantage was Shor's algorithm, which is for factoring, and generally kind of thought of in as applying to cryptography applications. And that's definitely out there, but it's really quite a bit bigger than that. So I think Feynman was the one who said the best way to simulate a quantum system is to use a quantum system. And quantum computers have potential to do things in chemical simulation and molecular simulation that are completely out of reach of high performance classical computers today. So simulating chemical reactions, it has applications to drug discovery, energy, weather, and climate, quite a long list. There's also a very broad class of problems in optimization and machine learning, which tie into things like computational finance, but actually almost every industry has very large, hard optimization problems that probably map really well onto quantum computers. And the third thing to realize is that progress is actually happening quite fast. So a decade ago, we were talking about sort of the first decent qubits and maybe getting towards demonstrations of decent like systems with multiple qubits. And now in 2021, we've gone past dozens of qubits, and we have many groups with many different types of hardware actually pushing towards hundreds of qubits and announcing plans for thousands in the very near future. And it's pretty clear that the pace is only accelerating. So I took a shot at mapping out the quantum computing ecosystem here. And obviously, it's way too large an ecosystem to have everyone on one slide. So there are lots of companies and groups left out. But the point is how to think about the categories. So there's a large class of companies that are building the QPUs themselves. And so these range from small startups to most of the very biggest companies in the world at this point. And one thing that's kind of interesting is there are many different types of quantum hardware, types of qubits, from superconducting circuits, trapped ions, silicon photonics, topological based qubits, and more. And it's really not clear who the eventual winner is going to be, or if there are going to be multiple winners. There's also a large class of companies building quantum software and quantum applications. And so these are things like the software stack to run quantum computers optimally, thinking about how to interface them with classical computers, which I'll get into, thinking about how to simulate them, and then also thinking about algorithms and applications, like how to map problems onto quantum algorithms onto quantum computers. Also, this is a talk at PASI. There are supercomputing centers and just national labs that are very, very interested in quantum computing. And so these are often centers with, of course, like very big high performance computational resources already, thinking about building large quantum systems and or integrating quantum systems as accelerators into their existing high performance computing setup for certain problems. Of course, like a lot of this is driven by academic researchers. So at most of the best universities in the world, there are people pushing the field forward. And then increasingly, there are a lot of industrial end users who sort of see that this is coming, see that they have problems that map very, very well onto quantum computing, and are partnering with quantum computing companies or starting their own groups. And this is a bunch of different industries, for finance, energy, automotive, drug development. It's a very long list. And so I also took a shot at sort of describing where I think the field is going. So we're entering a very exciting, I guess, passing through a very exciting phase. There have been a couple of demonstrations of something called quantum supremacy, which is a quantum computer solving some problem that would take a classical computer a very, very, very long time, or couldn't be solved at all. And Google demonstrated this first in 2019. Now USTC in China has also shown it. And so the problem here is a very contrived problem, not incredibly useful, and sort of designed to be something where quantum computers can best classical computers, but it's still a very important and exciting milestone. And so there's like tying this back to sort of where classical computers might fit in. A big question is, what's the limit of what can be simulated efficiently on supercomputers and GPU supercomputers? And so in the next few years, we're going to get into or maybe we already are in the noisy intermediate scale quantum era, where quantum gates are noisy. If you run a lot of quantum gates in a row, the errors accumulate, qubits lose coherence. But we're in a range of qubit count and performance where we can start looking for quantum advantage on valuable problems. And so it's a huge space of potential problems. And so there's going to be a ton of active research on hardware and on simulators to try to figure out, will noisy intermediate scale quantum computers have important quantum advantages on useful workloads, and what are going to be the best algorithms for that. And then finally, to run something like factoring, noisy quantum computers won't cut it anymore because you can't approximately factor a number. And so we'll need error-corrected, fault-tolerant quantum computing. And so this is definitely too big a topic to get into in this talk. But the idea is you can use many physical qubits, run what's called a quantum error correction algorithm, and have them function basically as one perfect logical qubit. And so once you start computing with logical qubits, errors are no longer a problem, and you can solve a quite bigger space of problems. So I think the important research here is, what are the best error correction algorithms? Like what tolerates best the noise of physical qubits to make the logical qubit with the fewest resources. Okay, so that was a very brief summary of what the industry looks like. But what does a quantum computer actually do? And so this is a massive oversimplification, but I think it can be sort of thought of in 3 steps. So first, you need a set of quantum bits, qubits, that can be put into superposition and entangled with each other. What does that mean? It means that they share a single quantum state, and it can't be sort of factored into a product with individual qubit states. And so this is actually a really powerful idea, and the reason that there's a speed up, because since they share a quantum state, that means for n qubits, it actually takes 2 to the n pieces of classical information to describe the entire state of the system. Okay, so that's sort of the quantum register. Then you need to operate on that register. And so that's sort of very analogous to what you do in classical computing with gates that manipulate the entangled state. And so you can have a single qubit gate to change the state of a single qubit. You can also have multiple qubit gates. Controlled NOT gate is a common example. There are also things like a swap gate and variations on that, where you're exchanging the information in 2 qubits. So that gives you a circuit, and then finally you need to read out the state. And so on a real quantum system, this actually your register is in a superposition state. Measuring it collapses and gives you some sample from that probabilistic superposition state, and then you run that many times, and you get a sense of what the distribution was. So how does classical supercomputing fit in, and especially how do GPUs fit in? Right now, I think there are 2 main areas we're thinking about in the short term for quantum circuit simulation. So real quantum hardware is sort of small and noisy right now. So classical simulators, if you want to do kind of research, like algorithm research on the biggest systems and the least error-free systems, classical simulators are the place to do it. And the second is for hybrid applications. So this is also a very big topic, but the sort of developing consensus in the industry is that certainly the first quantum applications and possibly all quantum applications will be hybrid, where the quantum computer is a resource that the classical computer calls to do certain things that it does well, and they sort of pass back and forth, kind of analogous to CPUs and GPUs today. And so you can imagine some of the sort of lessons and optimizations we've done to make that really effective will also be useful for controlling QPUs. Okay, so I'm gonna dig in a little bit on the quantum circuit simulation side and talk about cuQuantum. So cuQuantum is an SDK for GPU accelerated simulation of quantum circuits. And what that sort of looks like as a stack is you have a quantum application you want to run, let's say simulating quantum chemistry with a variational algorithm. Right now, there are many different quantum computing frameworks and developer environments run by sort of a lot of quantum computing companies. And so there you can define your circuit. That's sent to a quantum circuit simulator. And then cuQuantum sits underneath that with libraries to accelerate that. And it turns out that as I'll get into, like, these problems are very, very well suited for GPU acceleration. And so we're able to get large speedups running on the NVIDIA HPC stack on NVIDIA GPUs. And so what we're trying to accomplish with this is really to enable the research community. So we want algorithms researchers to be able to look at bigger circuits, to be able to do faster time to solution, quantum hardware researchers to understand sensitivity to the noise of their design. And then as we move towards fault tolerance quantum computing, people to be able to kind of research the best error correction algorithms. And maybe the best analogy, if you're in the AI space, is to cuDNN and cuPlus in AI. So there are all these problems in AI, a huge space. There's also a huge space of frameworks. Underneath all of them are cuDNN and cuPlus, which are NVIDIA libraries to accelerate all these problems and enable better research. And it turns out that the kind of math you need to do to simulate quantum circuits is very, very, very similar to like the kind of things you need to do for neural networks. And so the vision is for cuQuantum to do exactly this for the quantum community. And I'll maybe just briefly go through this since it's a little bit detailed. But basically, there are two main types of quantum circuit simulation. There's what's called state vector, where you basically hold the entire 2 to the n state vector in memory. The advantage of this is you have all the information. The disadvantage is, of course, the memory needs grow exponentially. And so even on the biggest supercomputers, you get limited somewhere in the 40s or up to 50 qubits. So there's kind of an upper bound, but this is sort of what you want to do for small numbers of qubits. To get to larger numbers of qubits, there's sort of a rapidly increasing popularity approach called tensor network simulation. And so basically the idea here is to model the entire circuit as a tensor network and then contract it step by step. And the effect is that you trade exponential scaling in system in qubit number for exponential scaling in circuit depth. And because most of the early candidates for quantum advantage are very shallow circuits, this is a trade that we're more than happy to make. And so tensor networks can actually allow you to push to hundreds or thousands of qubits for some problems. So I'll go through this really quickly. We'll have a library for state vector quantum circuit simulation. We expect in the first release, it will support single GPU, mostly with some multi-GPU APIs, user-defined gate application kernels, and the user will be able to control the memory of the state vector. We'll also have a tensor network library, and a lot of sort of our new contribution here is in an important problem in tensor network contraction, which is optimal pathfinding. So basically, once you define a tensor network, there are a lot of possible ways to contract it, and actually figuring out how to contract in the optimal path makes a huge difference in how well you can solve the problem. And so we do a bunch of pre-processing and optimization to get to sort of best-in-class performance in tensor network contraction. And so we have some early benchmarks to share. I'll say, first of all, that these are not apples to apples. This is a NVIDIA DGX A100 versus a dual AMD EPYC 7742 CPU. The problem here is random quantum circuits, which is the problem Google solved to show quantum supremacy. And so with the state vector method, we do up to 36 qubits because of the memory limitation, and a depth of 10, which is half of what Google did. For the tensor network simulation, this problem actually is really well suited. So we go to 53 qubits, which was a Google result, for in a depth of 20, which is the farthest, like the highest depth that they did. And basically in both simulations, we see more than 100x speed up over using a CPU. Tensor network is almost 1000x speed up. Again, not apples to apples, but also this was with a very early version of cuQuantum. This was done a few months ago. And as we get towards this release, we'll be rerunning these benchmarks, and we actually expect that this is sort of a lower bound on performance, and it should improve with the things that we've added. Okay, Brian, can I get a quick time check?
We're just slightly over. How much longer do you have?
So there's I can maybe this is a decent place to stop actually. There's an example paper that I wanted to talk about if I had a few minutes, but maybe I can just go to conclusions and provide the link to the paper.
Yeah,
that works.
You can do that. And I also currently don't have questions right now, but I do know Addison in the Q&A that's going to be coming up after we have Simone present. All
right, sounds good. So I'll skip through to the summary then. So quantum computing is a fundamentally new computing model with transformative potential in many industries. Current quantum hardware is making progress very quickly, but still a little bit small and error prone to achieve an advantage over classical computing on valuable problems. And so how do we get there? We need research to both understand and develop new quantum algorithms and improve and scale quantum hardware. And often simulators are the best choice of platform for that research. And then in particular, we think cuQuantum is going to enable scientific breakthroughs by allowing for much faster and more powerful simulations, expanding the space of algorithms that can be efficiently simulated. All right, so thanks for listening. Thanks for your time.
Thanks, Sam, and stay tuned for that Q&A.